Alrighty, howdy folks. Um, let's look at chapter 15, section 9. I know I have jumped a few sections with this. That's okay. Okay, so what is this about? This is about change of variables in multiple integrals. We have dealt with change of variables in regular integrals, that calculus one variable integrals, right? How did we do that? Let me show you. Suppose we have integral of f of u du. We say, if u were to be some g of x, then the way we deal with this is we say integral of f of g of x times g prime of x dx, right? And where u is g of x and du is g prime of x dx, basically. Now, if we go ahead and swap the variables, there's a reason why I'm doing this, because I want to be able to relate this to what happens if we have f of x. I'll tell you in a second. Okay, so integral f of x dx, then we can do something like this. Okay, now the reason is, what if we were to have f of x comma y dx dy? Because I wanted it in that form, which is one that's useful for us, let's go ahead and think of this original integral this way, is the whole simple idea. All right, and so where x equals g of u and dx is g prime of u du. Cool. What else? Well, one thing that mathematicians and mostly engineers usually do this, when x is some function of u, x equals g of u, would you agree that x is some function of u? What people do is they say, well, x is equal to x of u. What do you mean x equals x of u? You're just simply indicating that x is a function of u, some function of u. Okay. So if we adopt that notation, then we can say integral of f of x dx is nothing but earlier stuff. However, we can look at this as f of, instead of a g of u, we'll look at it as x of u. Right? That should make sense, right? Because g of u is nothing but x. X in this case is x of u. So g of u is x of u. For g prime of u, on the other hand, we'll say dx du, the derivative of x with respect to u, and I have this du here. So this is what I wanted to get to, so that I can relate this to the multivariable thing. So integral of f of x dx is nothing but integral of f of x of u dx du times du. Okay, look at this form and try to remember this form. Because when we get to change of variables in double integrals, and our objective is to find integral of f of x y dA over some region R, then that is the same as, instead of x, we have some x as a function of u and v. Say something like x equals g of u comma v. But then I'm trying not to use another function, simply saying x of u comma v. By that you should understand, oh, he actually means x is equal to some g of u of v, u comma v. Similarly, y is a function of u comma v. That means y equals some h of u comma v, right? So we have transformed x and y into variables u and v using some particular functions. And just as we had dx du here, the equivalent version in a multivariable thing is a bit more complicated. Instead of a simple dx du, we end up having an absolute value of partial x with partial of xy with respect to uv, partial with respect to uv of x comma y. So this is what is called Jacobian. And also, instead of a dx dy, we will obviously have a du dv. So this is something that you need to memorize. And also, let's watch this guy. How come r became s? That is to be expected, right? Our variables are no longer x and y. They are u and v. So that means the region that we were integrating in xy plane, in the xy system, is probably transformed to a different region. And that different region in uv is s. I don't know, man. That didn't make sense. Well, oh boy. It's something like this. If you make a u substitution, integral, let's say x plus 1, the quantity raised to 10 dx, then you say, and that integral is going from 0 to 1, let us say. Now when you transform that by substituting u equals x plus 1, can you say the limits are 0 to 1? No, you cannot. You have to convert the limits on x to limits on u. And in fact, if the relationship is u equals x plus 1, then x equals 0 means u equals 1, x equals 1 means u equals 2. So that integral from 0 to 1 actually becomes 1 to 2 because of the transformation u equals x plus 1. In the same way, the region gets transformed. The original region was R in the XY system. That region is transformed to S in the UV system. Okay? That's something to remember. Where F is continuous on region R. And X equals X of U comma V and Y indicating a change of variable from XY to UV. Okay? And S represents the transformed region in UV coordinate system of the region R in the XY coordinate system, like I was saying. All right. So basically, let's say we were supposed to integrate some function xy, f of xy, on this region R. Well, that same thing gets transformed to a different region S, like here. What is that? This is just arbitrary, but we will actually deal with specific cases or would be given to us, and from that we will figure out what S ought to be, the corresponding S ought to be, and all that. Okay. Now, this thing is what I need to talk about. This partial xy with respect to partial xy with respect to u and v, right? What is that? That is what is called a Jacobian. Jacobian is nothing but a determinant, a 2 by 2 determinant of a 2 by 2 matrix, and the entries of the matrix are partial x with respect to u in the first row and partial x with respect to v those are the first row elements, and partial y with respect to u, partial y with respect to v are the second row elements. You really have to sort of memorize this. Okay, so this is the Jacobian, and it is the equivalent version in the 1D is dx du. But here, because we have two variables, we have to use this Jacobian. Where did you get this from? Take a look at the book. The book has detailed explanation of it. I didn't want to show that and prove that in this thing. It takes way too much time. Okay, but understand the significance of this one. It's called a Jacobian. All right, so let's start working on some problems. Find the Jacobian of the transformation x equals u e to the v and y equals v e to the u. So Jacobian, all we need to do is find the Jacobian. Well, since the Jacobian is given by this particular determinant, I think it's fairly straightforward, a matter of plug and chug. That's what I wanted to show you. Cool. If x is equal to u e to the v, can you figure out partial x with respect to u? Well, treat v as a constant. So e to the v times the derivative of u is just 1. So partial x with respect to u is just e to the v. Okay, partial x with respect to v, treat u as a constant. So u times the derivative of e to the v is just e to the v. So partial x with respect to v turns out to be u e to the v, and so on. Similarly, partial y with respect to, we'll find each end. Partial x with respect to u, partial x with respect to v, blah, blah. The next thing we do is plug. So plug each of these things. You know how to find the determinant of a 2 by 2. Cross multiply these two things minus the product of those two. So that's all I did. E to the v times e to the u is e to the v plus u, or e to the u plus v. U minus uv e to the u plus v. We can factor out e to the u plus v, and so we get 1 minus uv. Cool? That's all there is to it. So this is how you find the Jacobian. Then let's look at another problem. Now let's actually do something. Find the image of the set S under the given transformation. So S is the square bounded by the lines u equals 0, u equals 1, v equals 0, and v equals 1. And the relationship between x, y, and uv is given to be x equals v, y equals u times 1 plus v square. Okay. What is this now? What this is saying is you have a region called u equals 0, bounded by u equals 0, u equals 1, v equals 0, v equals 1. That region must be transformed to an xy region. In the process of converting this UV region into an XY region, these are the specific transformations that you are expected to use. Okay, so without much further ado, basically what they're saying is, hey, suppose you have this region. Okay, does this region correspond to this stuff? Let's look. So we have a coordinate system UV. U equals 0. What does U equals 0 mean? Would you agree that that's the vertical line? This vertical line? U equals 0. Think of in the XY system, if I say, hey, boys and girls, draw the line x equals 0. X equals 0. Oh, that's the vertical line drawn at x equal to 0, right? So that's the y-axis. In the same way, u equals 0 is this vertical line. But the truth is, it should go all the way from negative infinity to positive infinity. It should not stop here. As such, if I simply say u equals 0, there is no need to stop between 0 and 1 like I have here. However, there is also this other restriction that v equals 0 to v equals 1. Those are the bounds. So v equals 0 means this point, and v equals 1 is that point. So it's just a line segment and not the entire vertical line. So that is u equals 0. Okay, and what does u equal 1 mean? Well, you draw a vertical line at u equals 1, which is this one. Again, this is also bound by those restrictions v equals 0 to v equals 1. So that's just a line segment as opposed to a full line. Now, v equals 0 is the horizontal line, and that's bounded by u equals 0 to u equals 1. So we have this simple line segment. Similarly, v equals 1 is this line segment. So what was given in terms of just u, we interpreted this in a geometric fashion. Now the question is, if this is what you are given, can you figure out what R ought to be? What region R in XY system is? What does this, let me put this, I'm sorry. What does this region transform to in the XY system, given that the relationship between X and XY and UV is this? Okay, that's what we are supposed to find. For that, let's proceed in a systematic way. Notice how I called this segment as S1, S2, S3, S4. So the way we'll do this is, we'll ask ourselves, what does this segment S1 transform to? What does segment S2 transform to? And so on. That's what we will try to do. Cool. So let's transform each line. S1 is given by V equals 0. Would you agree? The vertical dimension is 0 for this one, and it's bounded by u should be between 0 and 1. Right? That's what defines S1, the line segment S1. Cool. Now, how does it transform to XY? Well, clearly, we have X equals V. X equals V. But V is 0. So, would you agree? X equals V, since V is 0, must be equal to 0. And then we have Y equals U times 1 plus V square. Y equals U times 1 plus V square. What happens to that? U is something between 0 and 1, fine. V happens to be 0. So let's plug V equal to 0 into this. So when we plug V equals 0, this stuff in the parenthesis becomes just 1. So we have Y equals U, right? But then there are restrictions on U, that it is between 0 and 1. So this is what we will summarize now. We'll say X equals 0 and 0 less than or equal to Y less than 1. Okay. And the corresponding R1 is this line segment. Let's see if you agree with this. X equals 0. Oh, that's a vertical line. Are there any restrictions on Y? Yeah, Y is restricted to be between 0 and 1. So that's why it gets transformed to R1. Okay. Oh boy, I'm getting a cough, so let me pause this and get a drink. All right, let's get back. I don't need that. So it turned out that this segment S1 actually transformed to this vertical segment according to this transformation. Interesting. Now, let's go to S2 and see what happens to that. What is S2? S2 is basically U equals 1 and bounded by V between 0 and 1. Right? So, if we were to use the transformations, X equals V and Y apparently is U times 1 plus V square, but U happens to be 1. So if we plug that, Y is just simply 1 plus V square. So what's with this one? X equals V and Y equals 1 plus V square, and v is restricted to be between 0 and 1. So that means x is restricted to be between 0 and 1 since x equals v. All right. So another thing that we can recognize is y happens to be 1 plus v square, but v equals x, so we can say y equals 1 plus x square. Okay. What exactly did I do? Please pay attention to this part. What we eventually have to do is just have relationships between y and x. You should not have anything in u and v. You take these transformations, convert so that you have stuff with y and x only. Over here, we had x equal to 0. That was our line, end of the story. And there were bounds on the y. Here, we have y equals 1 plus x square. And the bounds on x are that x lies between 0 and 1. Right? So, use all the transformations and eventually get to this thing. Now, we are not done yet. We need to now interpret this graphically. What do we mean by y equals 1 plus x square? Do we have any idea what that graph looks like? Well, if you recall transformations, first let's ask, do you know how the graph of y equals x square looks like? Oh, that's a parabola. Cool. What is y equals x square plus 1? What does that plus 1 do? Well, it makes this one scoot up by 1, right? So y equals 1 plus x square is just a parabola that is scooted from 0, 0. The vertex would be at 0, 1, right? And the restrictions on x are that x lies between 0 and 1. So that's how it looks. Cool. How far up does it go? Well, maximum value of x here is 1. So 1 plus 1 square is 2. Oh, so that point has a coordinate of 1, 2. X equals 1, y equals 2. Cool. So what happened? This S2, line segment S2, actually became a parabola under this transformation. Cool. You must understand all of these things because next we are going to apply all of this to actually solving integrals. Okay, fine. Now what else? S3. Let's pick S3. What is S3, folks? It's a horizontal line. So that means V must be equal to what? What is the ordinate value? 1. So V equals 1 and restrictions, well, U should lie between 0 and 1. So that's what S3 is. Again, X equals V equals 1. Y equals U times 1 plus V square. If you plug V equals 1, then we have 1 plus 1 is 2, so 2U. So we have X equals V equals 1, Y equals 2U. Fine. Can we derive a relationship between, and also U is between 0 and 1? Fine. Can we now figure out how Y and X are related? Right? So X equals 1, that's fixed. And Y equals, X equals 1. And then Y is 2U, we said. What am I talking about? So Y is 2U. So maybe I should have had Y equals 2X here. 2X equals V. No. Wait. Got it. For a second, I confused myself. So, the equation is x equals 1. However, the y equals 2u part, what that does is it allows us to figure out the bounds on y. Y happens to be 2u, but u happens to be between 0 and 1. So 2 times 0 is a lower bound for y, and upper bound is 2 times 1. So we have 0 less than or equal to y less than or equal to 2. So we have x equals 1. Do you know what x equals 1 is? Oh, it's a vertical line drawn at x equals 1. And what are the bounds on that? Y should be between 0 and 2. So that gives you this R3. Right? Cool. Similarly, if you go to S4, where u is 0 and 0 less than or equal to v less than or equal to 1, then x equals v and y equals 0. And that means y is 0 and the restrictions on x are that x better lie between 0 and 1 because x equals v. End of the story. Okay, and what does that look like? Y equals 0. That's a horizontal line. Between what? Between x equals 0 and x equals 1. So that's R4. Whew. Right? So you must learn how to transform a certain region in one coordinate system to another coordinate system. So this problem is just simply transforming one region to another region in coordinate systems. Next, what we are going to do is actually solve integrals where this becomes a small part of it. And also, you need to find a Jacobian, which was the whole problem was finding a Jacobian in the previous one. That becomes a small part. So we'll have to put together a whole bunch of things now. So here is a problem. Fortunately, they are telling us what transformation to apply. Sometimes they don't even do that and they expect us to figure out the transformation. Okay, so we apparently need to evaluate integral of 4x plus 8y dA over a certain region R, and that region R happens to be a parallelogram with vertices these. And then we apparently need to use this transformation to figure that integral out. Do you see what the problem is? Okay, let me draw some figures, hopefully. So the region that we are given is this parallelogram. And we need to integrate this function 4x plus 8y in this region. Have we done anything like this before? Doesn't it look pretty simple? dA, dx dy. The problem, however, is this type 1 or type 2? Well, neither. Right? In a sense, if we go from, do we integrate along x first or do we integrate along y? If you want to integrate along x, the problem is we have maybe I should, okay, I got it. Oof, thanks. I got this picture done. So if you want to treat it as, I want to integrate along x first, then you must split this rectangle into two rectangles, into two triangles like this, two regions rather. That is because imagine you putting a representative rectangle which is vertical to indicate that you are going to scoot that rectangle all the way from the left to the right. So each time you're going to, let me put it this, sorry. First, you will put a vertical rectangle here almost at the left end. Figure out what the integral would be for that rectangular region. Then scoot that a little bit to the right, and then do again the integration, and you keep doing that from all the way from left to the right. That's how we are expected to do the integral. But the problem we bump into is when we try to do that, the width of the rectangle is dx. That's not an issue. What about the height of the rectangle? The height of the rectangle, unfortunately, is governed by the top portion is governed by that curve, that slanted line, and the bottom is governed by this other equation, by this line. Up to where that's not what it would be throughout. That is only true from x equals -1 to x equals 1. But when you go from x equals 1 to x equals 3, now your height of your rectangle is governed by two different curves. Not these two curves, but these two curves. Right? So that is what the problem is. If you wanted to do it by the methods that we knew, it's not impossible. We don't have to convert this. If we can split this into two regions rather, I shouldn't say intervals, two regions, and then integrate over them, yep, that's a possibility. Right? But that is what is involved in figuring out this integral, because the region is not a nice type 1 or type 2. However, what you will learn is, by using this transformation, the region will become a nice rectangle or square or some nice thing, and life becomes somewhat easier. Okay, that's the whole idea. So let's get busy. So let's transform each line. We have R1. Well, R1, all we know is this line segment is R1. So we have to figure out what that is. So for that, do you remember this 2-point form of a line? Right? You need to do 2-point form of the line, which is y minus y1 equals y2 minus y1 over x2 minus x1 times x minus x1, right? So y minus, you pick a point y1, let's say we call this as x1 y1. I don't remember if that's what I call. Yeah, I took this to be x1 and that to be y1 and this to be x2 and this is y2. So y minus y1, y minus 3 equals y2 minus y1. y2 is -3 minus y1 is 3 over x2 minus x1, 1 minus -1 times x minus x1. You better be clear in your head. You don't want to be swapping things. You don't want to say y minus y1 on the left hand side, but somehow use x minus x2 on the right hand side. So be sure to stay consistent. Okay. So that's going to be, and if you simplify this ends up being 3x plus y equals 0. Oh, that R1 has an equation is nothing but 3x plus y equals 0. Now let's transform it into let's plug these transformations. X is replaced by 1/4 u plus v and y is replaced by 1/4 v minus 3u equals 0. So now if you simplify this, what do we get? 3/4 u here minus 3/4 u. Now that cancels.
Are you with me? 3/4 u minus 3/4 u, that's just 0. 3/4 v plus 1/4 v. Oh, that's v. So this whole thing just becomes v on the left hand side. And so this means this is v equals 0. Isn't that cool? So what was this slanted line with a complicated equation governing it is just simply v equals 0 with this particular transformation. And that's a good thing. Similarly, R2, I did the same thing. Y minus y1 equals m times, or m is this one. So I think you get the idea. Right. So S2 turns out to be u equals 4. And similarly, R3 becomes S3 equals v equals 8, and this one. Okay. So one final summary sort of a thing so far as the region is concerned. What was the original parallelogram here converted into a nice, is this a square or a rectangle? 8, yep. Its dimensions are -4 to 4. That length must be 8 then. And 0 to 8, yeah, that's also 8. Yep, it is a square. Right? So S1 is this line segment v equals 0 from -4 to 4, and so on. So now, step 2, step 1 was to transform the region. You had a certain region in XY. What is it going to be in UV? Applying the transformation. That was our step 1. The step 2 is to find the Jacobian. Any idea why we are doing all these steps? Let me go back and show you. To be able to evaluate this integral, we have to do this. Think of this as f of xy. We need to convert this into f of uv times the Jacobian times du dv, right? So first, and the region needs to be transformed to S. So that's why we are proceeding in a systematic way where the step 1 is we are transforming the region. Step 2 is we are finding the Jacobian. Okay. And so Jacobian, remember what was the Jacobian? Partial x with respect to u, partial x with respect to v in the first row, and so on. So that turns out to be this. Determinant, cross multiply, this thing, turns out to be 1/4. Are we okay? Next. Oh, by the way, like I said, each of these, transforming the regions and finding the Jacobian, was a whole problem in the previous 2 cases. Now they form a small part of a big problem. Cool. And the third step is to convert that integrand into a function of uv. Okay, what do I mean by that? The integrand was 4x plus 8y. You can no longer leave it in terms of x and y. You have to figure out what it would be in terms of u and v. So that part is more or less straightforward. 4 times, for x we plugging this, and for y we plug this. And if you simplify, it turns out to be a -5u plus 3v. Cool? All right. What's the 4th step? Yeah, just go ahead and do the integral. What's that? Originally we had this over a region R. Then you need to transform the region, and you need to change the integrand from f of xy to f of uv, some kind of function of uv, and also multiply by the absolute value of the Jacobian. Now pay attention to this part.
let me ask you to be careful here. This is a tad confusing, not a whole lot, which is when I say absolute value here, am I saying absolute value or am I saying determinant? The thing is, this is actually absolute value. This is not determinant. Why do you say that, man? Because is the stuff inside, is this a matrix? No, it's not a matrix. Is partial x y over partial u v, is this a matrix? No, it's just over this. So that means I must mean absolute value here. Now, what the slightly confusing part of it is, I agree, is this stupid thing itself is actually a determinant, right? So earlier we found a determinant. This is, notice, I don't have an absolute value here. That is just the determinant is given, that Jacobian is given by the determinant here. And after we find the determinant, I'm saying we actually need to take the absolute value of this 1/4. Okay. All right. So I'll try to be careful about that. So 4x plus 8y, that integrand transformed to negative 5u plus 3v. So that part is this f of x comma y is this. Absolute value of the determinant, du dv. Right? Well, that's fine. But I also need to talk about the region S next. So let's recall. What was that region S? Region S, after we transformed from or the XY system to the UV, turned out to be this guy. So now is this region like a type 1 or type 2? Yeah, rectangles, vertical with the segments being nice horizontal and vertical. They are our friends, right? So this makes the fact that the region got transformed into a nice vertically oriented rectangle or a square made life easy here. So we'll apply the principles that we learned before. The limits on v, outer ones, the outside integral is v, and so my outer limits are on v. They are from 0 to 8. The inner limits are on u, and u is going from negative 4 to positive 4. So that's what I have. And we integrate. The rest, that part is, I yanked that 1/4 outside. The integral of u is u square over 2. Initially, I'm integrating with respect to u. So I'm thinking of v as a constant. So I have 3uv. And I'll apply the limits negative 4 to 4. And when I do that and simplify, we end up getting this, and we'll integrate from 0 to 8. That turns out to be 192. Oh man, this is pretty laborious. Welcome to college. Do we ever do stuff like this? Oh, you bet. You bet. You chemical engineers or even civils, mechanicals, you'd be using these kind of things in fluid flow, right? Fluid is flowing through some particular region with a given flow rate, and you need to find out when it comes out how much volume is coming out. So places like that, you will have to integrate over a region, and you will have to use stuff like this. So this is actually practically pretty useful stuff. Cool? All right, let's move on to the next one. So use the given transformation to evaluate this integral.
So they want us to evaluate this integral over a region R. And what is that region? The region is bounded by the ellipse. Apparently, the region is just an ellipse, the stuff inside and on the ellipse. And the transformation they want us to use is this. Cool? Step 1. What was step 1? Step 1 was to convert the region from R to an S. R right now is this ellipse. Can we find what the corresponding S would be? By the way, that region happens to be, and this ellipse happens to be oriented like this. So, can we integrate on this region? Right? Some weird region like that. Is this type 1 or type 2? Well, the problem is we can go from here to here, from the x equals whatever. Oh, wow. Do we even know what the left extreme value is? We don't even know that. Do we know what the right extreme is? Because I have GeoGebra, I was able to plot this on this one. So we don't even know what the left limit and the right limit of x are, nor do we know what the y limits are. Of course, we can do some differentiation and figure out maximum, minimum values and all that stuff. But then, what is the equation of that top portion of the curve? And what is the equation of the bottom portion of the curve if we are thinking of erecting a rectangle, a vertical rectangle, and scooting it all the way from leftmost point to the rightmost point? Man, that's going to be a nightmare. Right? So because of the weirdness of our region, we are having to resort to some transformation. That may not have been obvious now, but let me tell you that that's what is prompting us to resort to transformation. So hopefully, when we use this particular transformation, what we get in terms of u and v is a much nicer region. I don't know what that region is as yet. I lied because I worked this problem out, I know. But hopefully, it'll turn out to be a nice region. So first order of business is what? Step 1 was what? Convert the region R into a region S, right? So, in the UV system. Good. Now, notice our region is just bounded by one single curve, an elliptic curve. Okay? So we'll directly transform that curve. We'll say, this guy, what happens to this guy in terms of u and v? By plugging x equals this and y equals this. Oh, brother. So that turns out to be blah, 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 blah. And then you multiply all of this out. And it turns out this simplifies to a nice u square plus v square is less than or equal to 1. Okay. Is that a nice one? Yeah, that's just a circle, man. Right? The interior of a circle, less than or equal to, so both the boundary and the interior of a circle. So that actually transformed to this region. Are things easy to integrate when you have a region like this, a circular region, as opposed to a weirdly oriented ellipse? Answer is yes. It is much easier. Cool. Next, find the Jacobian. You remember? All right, Jacobian. That stupid thing. This determinant. So partial x with respect to u is square root of 2. The derivative of this is going to be 0 because we are differentiating partially with respect to u. This second term's derivative is 0, and so on. I won't waste your time going through just simple differentiation. And then when we multiply and cross multiply minus this cross multiply, that turns out to be 4 over square root of 3. I know. Mathematicians make a big deal about, oh, you can't have radicals in the denominator. Forget that. 4 over square root of 3. Cool. So that's the Jacobian. And the third, remember what the third step was? You got to convert the integrand from xy to uv. So let's get busy with that part. Convert the integrand into a function of uv using this particular transformation. The integrand turns out to be this. We already did this part. Okay. So the only thing was we had it equal to 2. Now we don't have it equal to 2. So that turns out to be 2 times u square plus v square. Good. So we figured out what the integrand would be in terms of u and v. And now let's just go ahead and integrate. Perform the integral. So this guy, and the original one in terms of x and y is this. F of x of uv, that part, would you agree, is 2 times u square plus v square. And Jacobian, absolute value of the Jacobian is absolute value of 4 over square root of 3 du dv. And the region, whatever that ellipse was, now gets transformed to this circle, u square plus v square less than or equal to 1. Uh-oh. Do we know how to integrate this guy over this region? This circle? Well, again, if you recall, polar coordinates actually helps us a lot. If we look at u square plus v square, convert it into polar coordinates, u equals r cosine theta, v equals r sine theta. If we do that, then this is simply 0 to 2 pi for the theta, and because this is a radius of 1, we go from 0 to 1. Right? And we have 2 times 4 over square root of 3 is 8 over square root of 3. I pulled that outside. For theta, we go from 0 to 2 pi because it's a full circle. And then the radius goes from 0 to 1. Right? And u square plus v square is just r square. And du dv, when we transform it, recall, you would have a r dr d theta. Do not say du dv equals dr d theta. That is terribly wrong. So r dr d theta is what we replace du dv with. And then the rest of it is straightforward. I integrated with respect to r first and plugged the limits on r, and that just ended up being 1. And 1/4. 1/4 minus 0 is 1/4. So that we have this, and 4 pi over square root of 3 is the final answer. Whew. I was pretty involved, right? Yep. Let's look at one more problem. Evaluate the integral by making an appropriate change of variables. Uh-oh. They're not even telling us what change of variables we need to apply. They're expecting us to figure out change of variables. Now, that is not so obvious, but fortunately, this is somewhat of a straightforward one. How should I put it? Well, in the real world out there, nobody's going to tell you what
what change of variable you need to apply. Okay. And that's when you need to be a bit clever about things. So you might try one change of variable, one set of changes, that may not work. You try another one. So basically it's a trial and error. Okay. So let's do this. By the way, that region that they said is x minus y equals 0, x minus y equals 2. This is what that region is bounded by, or it's a rectangle enclosed by these lines, which because of the bounds, it ends up being line segments. So this is how that rectangle is. Okay, what's the big deal, man? Why can't we just integrate? Again, this is not type 1 or type 2 unless you split this into different regions. You split the region into how many? Uh-oh. This stupid thing. You actually need to replace this into 3 regions if you were to draw a vertical line at this point. So that part would be one region, and then you need to draw a vertical line here, and between this vertical line and that vertical line is a second region, and there would be a third region between this vertical line all the way up to the right end point. So you have an option of splitting this into 3 separate regions and evaluating the integral, or you can apply some good transformation. So step 1, find appropriate change of variables. Looking at the integrand x plus y e to the x square minus y square. Okay. And also this x minus y equals 0, x minus y equals 2, x plus y equals 0, x plus y equals 3. Man, there are a whole bunch of what seems to happen is there are only x minus y's and x plus y's so far as the region is concerned. Similarly, even the integrand seems to contain x plus y's and wait, x square minus y square. Isn't that also x plus y times x minus y? So the whole thing seems to be governed by the stupid x plus y and x minus y. So that's a hint. Guided by those things, let's say I want to try the transformation u equals x minus y and v equals x plus y. Okay? Will it always turn out to be something straightforward like this? Unfortunately, no. But that's the idea. At least for this is the thought process. Cool? All right. And step 2 is transforming the region. Well, actually, in previously, this was step 1, right? Transforming the region. But here that gets scooted over to step 2 because step 1, we don't even know what the change of variables should be. So what was step 1 now became step 2. That means what? Whoa. Was it that simple? Dang. It is that simple, isn't it? The first one is x minus y equals 0, but x minus y is u. So basically that thing is just u equals 0. Hey, that is nice. X minus y equals 2. That means u equals 2. This is v equals 0. That's v equals 3. Ta-da! Wow. That part turned out to be somewhat straightforward. And I went ahead and drew that region. So what was this weirdly oriented rectangle has now become a nice vertical horizontal rectangle. And that's a good thing, right? Cool. Jacobian, straightforward.
Not so man. Jacobian expects you to have x in terms of u and v, and similarly y in terms of u and v, but that's not what we have. We have u in terms of x and y and v in terms of x and y. So we need to figure out, we need to go the other way. Well, can you solve for x in terms of u and v? What if you were to add u plus v? Then negative y and plus y add up to 0 and you get a 2x. So 2x is u plus v. So x equals 1/2 of u plus v. Similarly, if you subtract, you get 1/2 u minus v. That's y. So now we are ready for the Jacobian. Partial x with respect to u is 1/2 and so on. And this turns out to be negative 1/2. Wait. Can the determinant of a matrix be negative? Of course it can be. Right? So there is no surprise that this determinant of a matrix ended up being negative. And in fact, this is precisely why when we do the integral, we take the absolute value of the Jacobian. Now you see, do not say the absolute value of, do not say just the Jacobian and say negative 1/2 in your integral. You better take the absolute value of the Jacobian. So be sure to make it 1/2, positive 1/2. Okay. All right. Convert the integrand. Right. Is that straightforward? X plus y. We're going to replace with v. E to the xy. V e to the x. uv. X square minus y square is x plus y times x minus y. So that would be u times v. So basically v e to the uv. Would you agree? So that becomes x plus y. Did I goof? Crud. That should be a V. Samuel. I'll fix that. Okay, but just let me allow me to go through the process and I'll fix it. So u e to the uv or v e to the uv, just a matter of integrating from 0 to 3 and 0 to 2. Okay, so that eventually turns out to be, I hope that's what this turns out to be. The process, I hope, is at least straightforward. Okay. In the notes that I have associated with this, I'll definitely do the fix and go from there. Okay, folks. Alrighty, sorry about my mistake. That concludes chapter 15. Okay, fine.